I simply want to talk about an algorithm and an idea that is a very recent algorithm, and in connection to this, questions about scalability of algorithms for reinforcement learning or planning. In this case, it's just planning. So let's get started. So this is joint work with Gellert, Philip, Barnabas, Yassin, and Nan. And most of the work was done by Gellert. Oh, and you see the link to the archive paper. You can ask me in the chat for the link later if you're interested in this paper. And in terms of the contents, it's a simple talk. It's a tea time talk. It should be short. Should be one clear message. So here we're going to talk about planning under in large MDPs when you have a linear functional approximator that is able to represent the optimal value function with a few coefficients, and you're asking whether there exists an efficient planning algorithm for this case. And I'm going to present a new method. We call it TensorPlan, and we'll make the claim that this is efficient, and then we'll sketch the argument of why this method is actually working and why it has the guarantees that it does have. And I'm going to spend some time on probably making the point that this algorithm is a little bit unlike your usual dynamic programming algorithms. And why is that? And do we believe that you need something, you need to go beyond dynamic programming or not? So is there anything wrong with just dynamic programming? ADP stands for approximate dynamic programming when you use functional approximation. So the context is just MDPs. Everyone knows MDPs. You have states, action, transitions, rewards. It's a finite horizon setting. You have finitely many states. You have finitely many actions. But don't worry, the number of states is going to be huge. So we are going to ask the question like, can you have a planner which scales to really large MDPs? So algorithms whose runtime scales in any form with the number of states are not going to be acceptable. You will see how we do this. The answer is going to be yes in this case. You can have something like that. So you have the transition probabilities and the rewards. The rewards, the RSA is just a real number, simplifying things a little bit. PSA is just the transition. It's just the probability distribution over the next states. You have the value functions. Since it's the finite horizon setting, value functions are indexed by the stage. You have the optimal value function. Your goal is to find a policy which is nearly optimal with respect to whatever initial state you find yourself in. That's generally the goal. And usually the way we think about solving this goal is that we can just solve for the optimal value function, which is going to be for every stage, a function that assigns values to states, and then just do one-step look-aheads, these Bellman look-aheads, and then find out the maximizing action. So that's shown in the bottom here of the graph of the slide. And how are we going to deal with large state spaces? Is that we're going to assume that some friendly oracle passes us a bunch of features, like whatever state we find ourselves in, whatever stage of the decision process we are in, we are given a feature vector, and we are also given the promise that the optimal value function at that state can be written as a linear combination of the feature vector components that are specific to that state. And then the question is, okay, like this seems to be an advantageous situation because, well, we expect the number of components, the number of basis functions to be much, much smaller than the number of states times the horizon, let's say. And we know that if you knew the optimal value function, then you could do this one-step look ahead and you would have the optimal policy. You only have to find out D numbers, regardless of the number of states. So this is like the advantageous situation that we find ourselves in. The question is there an algorithm that can take advantage of this or not? And again, the way we often think about this is that, well, we could just like try to solve for the optimal value function. We have these optimality equations, Bellman's optimality equations, that are satisfied at all the states and all the stages. And these equations depend on just the coefficients, the unknown coefficients now. And there are many, many equations. It is an overdetermined system of equations. So maybe we can just somehow efficiently find out these d coefficients and then call it a day. So that's the question. Is there such an algorithm? So what is the setting to be more specific? We're talking about local planning and local access to these features. So this is like model predictive control, if you want. You have a simulator that you can access, and the simulator actually is correctly representing the word. And every time the word is in some state, the state information and the associated feature information is passed to the planner. The planner can then consult the simulator and ask queries about like what would happen given that I have seen this state. I would take this action. What would be a next state? Give me a next state from the next state distribution. What is the associated reward? What is the feature vector at this next state? So these are the forms of individual queries that the planner can use. It uses these queries for a while. Eventually, it has to come up with some action. Once it came up with the action, this action is fed back to the word, which is the same as like what the simulator also represents. And the word moves on to the next state. So I call this local planner because the planner is past the state and it's not asked for designing an optimal policy. It is asked to come up with a good action such that if you continuously do this planning, and so it's important that for every state transition, you can call the planner and the planner can do computation. It can collect more information from the simulator, from this generative model of the word. And it has only come up with an action. And then once the action is computed, the word moves on. You do this in this continuous loop. And you're asking that the planner, the policy that the planner induces this way should be a good policy, right? Like a good planner is the one that if it's used in this continuous manner, in a closed loop fashion, and there is no discrepancy between the word and the simulator, then this leads to good policy, good behavior, like lots of reward, right? So that's kind of obvious. And it's called local because it's like the computation is localized, like we are monetizing computation. And it's like, it seems like that we should be doing this anyways, if we can. And I also say that we have local access to the features. So you can't just do a big pre-processing of the feature map because that would involve like, like naming states that you have never seen. And that's not legit in this setting, all right? All right, any questions for this? Is this clear? Good. All right, so, okay, like every talk these days have to have a video. So I went on the internet, found this video. It kind of captures the feeling of what's happening. So in control, this mode of continuously using a planner is called model-predictive control. And like people use it a lot. So it just like shows this autonomous driving car, self-driving car, doing this planning for a fixed horizon. In my setting, the horizon is like fixed and like it's not a continuing problem. So, and every time the planner is called, you move down one stage to the end, and like after 8 steps, it's like the game is over, right? So it's like that's a little bit of a difference because here the horizon is kind of a rolling horizon in this example. In my word, it's not a rolling horizon, it's just a fixed horizon. I'm simplifying things. You could do the rolling horizon thing, and sometimes it could work. Like I'm not talking about that. All right. So besides, Yeah.
Are you thinking of planning as something that proceeds incrementally and is accumulating some value function, or is it like model?
It can, yeah, it can have memory. The planner can have memory, and it does have memory. It can keep information between the calls to it. Although the result allows for planners as well, so you could have a planner that doesn't do that, but that's a lazy way of doing it. It's better if it keeps the memory, and like the way I think about it, it keeps memory. All right, so the main result is that there exists this algorithm, which we call TensorPlan. You will see why, that says that no matter what MDP feature map pair the algorithm needs to work with, it's a good algorithm, and it doesn't use a lot of computation per call. That's the result. Right? The algorithm has an input parameter. It's like the target suboptimality. And if you make this suboptimality smaller, then the cost is going to go up. The number of queries that the algorithm uses, in particular, is going to scale with dh. D is the number of features, age is horizon, divided by this target suboptimality data. And then, yeah, you see it right. It's to the power of A. A is the number of actions. So that might raise some eyebrows. Like, is this polytime? Well, for a fixed number of actions, this is polytime. Okay, that's like a little bit abuse of terminology there. But yeah, think about if you have just 2 actions. And this is quadratic in everything. So that's okay. We have to come back to this question of whether we like it or not, that the number of actions is in the exponent there, but this is the result that we can have at the moment. And if you only had 2 actions, this is an okay result. Like no other result existed before this that would be able to do even this for 2 actions. So I see that this is some progress. So that's the result. And actually, this algorithm is more powerful than what is stated in the first result. So in the first result, the statement was that, well, if the MDP feature map pair is nice and harmonic with each other, then things are nice. And that was with respect to the optimal value function. But actually, the algorithm can also work if some other policy has a linear representation with the features, and it can compete with all these policies. So it doesn't have to be the optimal policy, which is like, I think it's like greatly enlarging the scope of the algorithm. Because the optimal value function, maybe it's too narrow, like it's hard to capture that. Anyways, so that's the refinement of the result. And finally, if the value functions are not exactly representable, but only approximately representable, the algorithm has to pay a price for it, but it's going to be a graceful degradation. It's not too harsh. It's like, yeah, it's not necessarily a small price, but it's not like that. You have some tiny errors, then it's suddenly everything is gone. It's a continuous function of the error, like the performance degradation, or like it's like everything is expressed in this case, like how much more compute you have to use to get to the same level. Then you have to use more. And the level is going to scale also with these approximation errors. All right. So how does the algorithm work? It's a generate and test algorithm. The hint is that, well, we have to focus on these D parameters because that's what we have, right? Like that's our only chance to have a good algorithm. Like somehow we have to come up with good parameters and then use them in some way. So the algorithm proposes some parameters. It proposes them optimistically, and I will explain it later. What do I mean by that? And once this parameter is proposed from a set of feasible parameters, the algorithm runs some checks. And these checks are, in a way, trying to check whether some consistency criterion with these parameters with respect to some version of the Bellman equation is met. And if the check pass, then the algorithm says, I'm done, and returns with the current parameter and the underlying induced policy. And it takes the action that this policy suggests, and then the word moves on, and so on and so forth. In the other case, if the test fails, then the algorithm collects some information that it adds to the information that it keeps track of, that restricts the set of feasible parameters. So this new information restricts the set of feasible parameters, and then the whole process repeats. You have a smaller feasible set of parameters. You optimistically choose another parameter. You generate these rollouts with the induced policy. If along the rollouts you see some contradictions with your expectations, then you repeat and otherwise return. Okay, so what's the optimistic choice? So the optimistic choice, very simply, is that you are at this state S0, where you need to return an action. That is the set of feasible parameters. This is this capital theta set. It leaves, it's a subset of the d-dimensional space. And amongst this set, you just choose the parameter that maximizes the value, the predicted value at the current state. What is the predicted value at the current state? It's the inner product of the parameter vector and the feature vector that we are given at the current state. All right, so that's like a linear optimization problem over the set of feasible parameter vectors. So that clears up what optimistic choices are. And then the question is, what is an induced policy? The induced policy for the full version of TensorPlan is the one which chooses any action which is consistent with the parameter vectors as written like with this equation that makes this equation true. And of course, in reality, you don't expect this equation to be true, so there's going to be some errors. So you'll lose some lag, but like I'm not going to go into the fine details of like how much lag you will lose between the parameters, between the left-hand side and the right-hand side. But okay, like the idea is that you choose any action that makes this equation satisfied, and any such action defines this induced policy, and then the rollouts are done with this induced policy. Okay. To find these actions, the algorithm is using the simulator to generate samples from the next state distributions, which are not available. So it like has a current state in its rollout. It tries all the actions and then looks for an action that would make this equation satisfied. And if it finds some action like that, then it's happy. It just takes that action in the simulator and then rolls with it. And it does this until it arrives at a state when no such action exists. And then it says that, well, this is interesting, this is surprising. I generated some data with which the current hypothesis about a parameter can be rejected. So I'm going to reduce my hypothesis space or version space. So that's what the algorithm does. All right, so my time's kind of up. So why will TensorPlan stop changing theta, and why do we use this weird construction for defining the induced policy? By definition, the induced policy is well defined if all the TD errors at all the states and actions are zero for some action, which is equivalent to that the product of these TD errors over the actions at some state is zero. And you can just like write this, rewrite it with linear algebra, and it becomes a linear expression in the tensorization of the parameter vector. So that's just like moving the unknowns to one side. And now if you look at this, this is just linear constraints on a polynomial function of the parameters. So you basically lift it to a higher dimensional space, but there you have linear constraints. You are measuring the left-hand side of the inner product, and you're guessing the right-hand side. So you have this discriminants. And how many unknowns do we have? We have d to the power of a unknowns. So then, like with some messaging, you can conclude that after d to the power of a measurements, you will get the parameter vector. You cannot run into contradictions more than that many times, roughly. Okay, so that's why all these choices, will it induce a good policy? Well, the optimistic choice of TensorPlan makes it induce the best policy amongst the all inducible policies. Okay, because it always shoots for the highest initial value. So that's where the desire to maximize the rewards comes in, and that's how the optimism makes sense. Like if you take away this optimism, then this pressure is gone. No pressure on choosing a good policy, and then TensorPlan could end up with a very bad policy. All right. So dynamic programming. Well, okay. First of all, you could change the consistency to a place to just roll with the dynamic programming equation as we know from Bellman. That wouldn't change. I mean, like, so the algorithm still works. It has a narrower scope because now it can only work if the optimal policy has a linear representation or near linear representation. So that's a narrower scope, but it would be faster because it can reject hypotheses faster. So it would be, I would say, marginally faster. So you cannot really uniformly improve the speed, but on some instances it could run faster, and you could do something in between these two extremes as well. But this is still not DP, because in classical DP you are doing value propagation, you're doing these updates, and this algorithm is not doing that. It's kind of like thinking globally about the parameter space and then how to reject stuff there, and then adds optimism on the stuff. So there is a lot going on. And if you think about this back propagation of values, we are not able to prove any similar nice results. The errors can just blow up, like these extrapolation errors compound. And in previous papers, we were trying to construct lower bounds. For this setting, we don't have a lower bounds for the DP algorithms, but we're working on it. I think that DP algorithms are just not going to cut it. Right, closing thoughts, optimism is not new. What happens with Q-star linear realizability, that was done a while ago by Zheng Wen and Ben Van Roy. So for deterministic systems, it's pretty weird. Like for Q-star realizability for deterministic systems, the optimistic algorithms are computationally efficient, they're sample efficient, they work online. Deterministic systems are awesome. It's weird. So for stochastic systems, we had a paper with Galliard and Phil that says that the same result doesn't go through. Just there is no algorithm that would do the same thing for stochastic systems. So there's this huge separation between stochastic and deterministic there. So it's kind of weird. I didn't say that TensorPlan was computationally efficient, and that was no coincidence. We don't know whether it is, or there would be an algorithm that is also computationally efficient for this setting. So does it work? Is it implementable? I don't know. And there are many other questions. All right. Done.
Thank you, Csaba. So I guess we'll just open for questions.
Yeah, Rich.
So I have a question about the like on early in the, sometimes you have these inner products of PSA with something, and it wasn't, it seemed like sometimes it was different. Like here, it's an inner product. So those are
yes.
Those are vectors
Okay.
of the entire state space.
Yeah, it is. It's a value function. It's like treated as a vector, right?
So isn't that too large to compute?
Yeah, you're just sampling. So the actual algorithm will use sampling to replace all these inner products. And the actual proof takes care of that the sampling errors do not compound. Yeah. Good point. Yeah, I tried to quickly mention that, but I guess it was just too implicit. But you have, yeah, it's correct. Like that would be too large. that's the main problem. And so, but luckily, these errors don't compound. So in a way, this whole thing is about the stability of the optimality equation as a function of like the errors when you are perturbing transition probabilities and rewards, let's say. Rewards usually don't matter that much, but you want to know that if I approximately know the transition probabilities, does that imply that I approximately know the parameter vectors, or can I get like some really bad spurious solutions? And the answer based on this tensorization construction is that these equations are stable. But it's also kind of, I think it's similar to what happens in numerical analysis as well, where like you could have an algorithm which is doing elimination in a particular order. I think that that's similar to what dynamic programming does. And that's not necessarily numerically stable. Then you can blow up the errors. But if you globally look at the whole system of equations, and you say that like, let's solve for when all of these are the same, and like you properly treat the errors, so that's what happens in this algorithm, then stability arises.
I also have a question about, if you go back to the algorithm slide, I think I was just too slow in my thinking, but I was remained confused because we have the three things. We have theta plus, we have theta, and then we have the fancy theta.
Right. So we have the 6 theta, which is a set. Do you call that the fancy theta?
Yeah.
I guess that's the big theta, capital theta.
Okay, good. So
yes,
so chosen theta plus.
Theta plus is your choice of the parameter vector that comes from this big theta.
And then somehow we get theta. Where does the theta come from?
Oh, like in sub-item A?
Yeah.
Ignore that. That's theta plus.
That's theta plus? Okay.
You're not too slow, but too precisely reading things.
Too literal.
That's the other type of problem with people. They're too precise. Good. Thanks. I will fix it. Yeah.
So all these thetas are theta pluses.
Yeah. And actually you can get rid of A. Like you just check this consistency, because if consistency holds, then you also verify that you achieve the predicted value. So it's like you don't have to separately check that.
So if I understood correctly, you just do, let's say, Monte Carlo rollout, and then you find the parameters that find basically the value that is similar to the Monte Carlo rollout. So how do you find the value here? I'm confused.
Right. So yeah. So it's not on the slide. It didn't fit the slide. So when there is a failure, then we found a state such that for none of the actions, the current parameter vector satisfies the equation shown in the bottom. But we know that like the assumption is that there is a parameter vector that satisfies the equation. So we just like add this as a new constraint. So it's a constraint generation thing. We add this as a new constraint, and the new parameter, like the new set, is also constrained by this data that we just generated. Does it make sense? It's like the algorithm is selectively collecting surprising data. It runs the rollouts. When it's surprised, then it says, this shouldn't have happened. Let me keep this data. So it's kind of neat as well, because it generates more data than it keeps. It only keeps the ones that are surprising, where there is a contradiction. But it sees that this equation is not satisfied, It says, oh, okay, like I need to satisfy this equation. So let me go back and replan. Like this whole thing is wrong, but I believe it's going to work. It's not working. I need to adjust.
Okay, I think I see a bit better it.
Yeah,
Thanks.
yeah. I mean, a paper has the glory details. Brandon?
Yeah, so I was just wondering, specifically about how the graceful degradation behaves, like in terms of what your error model is, because a single large error would seem like it would have a, it would cause it to be completely inconsistent, which would lead it to keep.
So the error model is uniform error, so max error. So if you call the max error epsilon, then you pay a penalty of, I don't know, epsilon square root d and some polynomial of h. I don't remember. That's what you pay. That's what you pay in suboptimality.
Okay.
Sorry, a question about notation actually. So here, it seems that there is only a set of parameters for so the value function at time 0 and also value function at time 1 and so on, or
the parameters shared across the different stages. Okay. The feature vectors are different.
Okay, I see. Thanks.
Yeah. I like parameter sharing. I think that that's the general approach.
I have another question too about the notation. Here on this slide, we have pi theta of s, and it returns a particular action. It seems like we might need to return a different action depending upon which stage we're at.
Yeah, that's a minor typo. Yeah, true. Okay. It is. So the policy is also indexed by the stage. That's right. Good. This is why I like this audience.
So you said that it wasn't clear if it was computationally feasible. So can you go into like which part is hard?
Tractable. Yeah, the optimistic optimization, this theta set, it's the theta set itself has a weird shape because it is like the polynomial function of the theta is subject to linear constraints. And so that's like a polynomial constraints on this set. So that can be a complex set. So it's not like what's shown here on the slide, not a nice ellipsoid, but it's probably just some weird set. And because of that, solving this linear optimization problem may be hard. So this optimistic step is often like we find that it can be challenging. Sometimes, like specific instances, it's intractable, but sometimes you can approximately solve it. And for example, for LQRs, there was a similar situation, and a recent paper, or maybe not so recent anymore, but just resolved it by relaxing the optimistic planning problem. And they're able to show that you can tractably solve this optimistic planning problem. But in this case, we didn't get that far. Like we don't know whether this can be done or not, or you would need to fundamentally change the algorithm to do something about this. Yeah.
Okay, so it looks like we're at the end of the 10-minute question period. Thank you, Csaba.
All right, I'm happy to hang out as usual. If people have other questions, I'll be around for a while. Thank you.